All right, in this video, we will be going over section 7.7. Section 7.7 is about alternating series. Okay, basically, we will be defining what we mean by an alternating series, and we will be going over some convergence properties of alternating series. Okay. All right, I want to start by defining an alternating series. Here is the definition. Let AK be a sequence of positive numbers. A series of the form sigma k goes from 1 to infinity minus 1 to the power k plus 1 times ak, or sigma k goes from 1 to infinity minus 1 to the power k times ak is called an alternating series. Okay, if a series takes one of these two forms, then we say that it's an alternating series. And notice that these ak's have to be positive terms. Okay. All right. Next, I want to go over this theorem, which is called the alternating series test. Okay, one of the most important theorems in this section. Here is the statement of the theorem. Let AK be a sequence of positive numbers. Again, this is extremely important. Okay, it has to be a sequence of AK has to be a sequence of positive numbers. And if AK plus 1 is less than AK for all k greater than or equal to 1, and this limit is equal to 0, then the conclusion is both of these alternating series are convergent. Okay, this series converges and this series also converges. Okay, that's the conclusion. If you look at the hypothesis or the conditions in this theorem, does this remind you something? The first condition, AK plus 1 is less than AK for all k greater than or equal to 1. What does that tell us? That means AK is a decreasing sequence of positive real numbers. Okay, this AK is if AK is a decreasing sequence of positive real numbers with this limit being 0, limit as k approaches to infinity, AK is equal to 0, then the conclusion is both of these alternating series are convergent. Okay, this summation, both summations exist as a real number. All right, that's what the theorem tells us. And then I want to walk you over this theorem, theorem 7.38 in the book. And this tells you how we can approximate the sum of an alternating series by partial sums. Okay. All right, let's go over the theorem. Let L be the sum of an alternating series. That is, either k goes from 1 to infinity minus 1 to the power k times ak is equal to L, or k goes from 1 to infinity minus 1 to the power k plus 1 times ak is equal to L. Okay, that satisfy ak plus 1 is less than ak for all k greater than or equal to 1, and this limit is equal to 0. Then for any term Sn, this is the nth partial sum. In the sequence of partial sums, this difference, absolute value of L minus Sn is less than an plus 1. Furthermore, the sign of the difference L minus Sn is the sign of the coefficient of an plus 1. Okay, when I say sign of the coefficient an plus 1 is you go to this series and then you find the k plus 1 term and check the sign of that. Okay, that is the sign of an plus 1. All right, so what does this tell us? This tells us that this difference, notice that this is the difference between L. L is the summation of the original series and Sn is the partial sum. Okay, difference between L and Sn is always less than an plus 1. Okay, absolute value of the difference between L and Sn is always less than an plus 1. And of course, this difference has the same sign as the sign of an plus 1 in the series. Okay, so that means if this an plus 1 is very small, that means the absolute value of this difference is very small, right? What does that tell you? That tells you that your Sn is very close to L if this number is very small. So we can use this as a sort of a criteria to approximate the sum of a series by the partial sum. if this number is a very small number, then the corresponding partial sum Sn is a very good approximation for L, because this difference of absolute value of the difference of L and Sn is less than this small number. Okay, that's the idea. Okay, all right. You can also view this as a kind of a tolerance to tell how close you want your Sn to be to L. All right, let's move on and let's go over this example to understand these two theorems. Okay, here is the example. Use the alternating series test to show that the series, this given series, converges and find an approximation to the sum within 10 to the power minus 6. Okay, we need to find an approximation to this sum within 10 to the power minus 6. Obviously, the approximation is going to be the partial sum, right? We need to find some Sn, some partial sum with suitable n, so that the partial sum approximates the original sum within 10 to the power minus 6. That's the goal. First of all, we need to show that this series converges. Okay, to show that it converges, I'm going to use the alternating series test. Recall that the alternating series tells us that if AK is a positive sequence of positive numbers, which is a decreasing sequence, of course, with this limit is equal to 0, then both of these alternating series are convergent. Okay, so clearly this is an alternating series. You should be able to see it because you have minus 1 to the power k here, right? And can you identify AK in this case? Remember, one form of an alternating series is k goes from 1 to infinity minus 1 to the power k times AK. If you compare this standard form to this one, can you identify your AK? Clearly, your AK in our case is going to be 1 over k factorial, right? It is everything except minus 1 to the power k. So you take off minus 1 to the power k, remaining thing will be your AK. Okay. Now, notice that AK plus 1 is 1 over k plus 1 factorial. To find AK plus 1, you replace this k by k plus 1, right? So you get AK plus 1. And notice that, first of all, this AK is a sequence of positive real numbers. No matter what number you put here, 1 over k factorial is always a positive number. So that's a good sign, because we are going to apply the alternating series test, which requires the terms of the sequence to be positive. That's good. So we need to check two more criteria. We need our sequence AK to be a decreasing sequence, and this limit has to be 0. Is that a decreasing sequence? Of course, yes. If you compare these two, look at these two, AK and AK plus 1. Clearly, AK plus 1 is strictly less than AK. Why is that? Because the denominator here is bigger than the denominator of this expression. That means AK plus 1 has to be strictly less than AK. Okay, so that condition is okay. What about the other one? Would the series converges, sequence converges to 0? As k goes to infinity, AK, what will happen to this? Limit k goes to infinity, 1 over k factorial. This is clearly 0, because as k goes to infinity, this k factorial means 1 times, 2 times, all the way up to k, right? That product is also approaching to infinity as k approaches to infinity. That means this takes the form 1 over infinity, that is 0. So both criteria of the alternating series are satisfied, and the terms of the series sequence is positive. So by alternating series test, we conclude that series test, the given series okay, this summation converges by alternating series test. Okay. Oh, by the way, here this is let's make this k goes from 1 to infinity. Okay. Please make that correction. K goes from 1 to infinity. All right. Next, we are supposed to find an approximation for the sum of the series. We know that this series converges now, but now we need to find an approximation for the sum of this series, okay? But from the previous theorem, from theorem 7.38, we know that absolute value of L minus Sn is less than An plus 1, okay? We are going to use this idea, this theorem, to find an approximation, okay? So we already know that absolute value of L minus Sn is less than An plus 1. Okay. Notice that L is the summation of the original series. The sum of this is equal to L. Okay. That's what I mean by L. L is the sum of the original series, the given series. And Sn is the, of course, the partial sum, nth partial sum. Okay. Let me define the Sn as well here. Sn is k goes from 1 to n minus 1 to the power k divided by k factorial. Okay. So if we have this, to find an approximation to the sum of the original series, what I need to do is I need to make sure that my An plus 1 is a small number. So I'm going to plug in various values for n and see when I get this number less than or equal to 10 to the power minus 6. I want my answer, my sum, to be within 10 to the power minus 6. To do that, I'm going to make sure that my An plus 1 is less than or equal to 10 to the power minus 6. If it is less than or equal to 10 to the power minus 6, the absolute value of this difference is less than 10 to the power minus 6. That means my sum is accurate within 10 to the power minus 10. Okay, my original sum is within 10 to the power minus 10 of the sequence of sum of the sequence of partial sums. Okay, nth partial sum. All right, so for that, I'm going to calculate some An values. Okay, first, when n is equal to 1, you will see that A1 is equal to 1 over 1 factorial, which is 1, which is of course not less than or equal to 10 to the power minus 6. Okay, I want that An plus 1 to be less than to 10 to the power minus 6. So I try some bigger numbers. Okay, n is equal to 2, 3, 4. Okay, I'm not going to try all those values, but I'll show you what we need here. Okay, if you try A9, this is going to be 1 over 9 factorial. But you will see that if you calculate this using a calculator, you will see that this is bigger than 10 to the power minus 6. But remember, I want this quantity to be smaller than 10 to the power minus 6 because I want to have my sum within 10 to the power minus 6 of its original value. Okay, or the absolute value of the difference between these two quantities has to be less than 10 to the power minus 6. Okay, but if I try here now a to the power A10, that is going to be 1 over 10 factorial, which is of course less than 10 to the power minus 6. So now this A10, we can view A10 as A9 plus 1. I'm writing 10 as 9 plus 1, which is less than 10 to the power minus 6. Now, as you can see, your value of n needed here is 9. Okay, so because we know that your An plus 1 is 10 to the power minus 6, and the absolute value of this difference is less than An plus 1, A9 plus 1. Okay, if you take n to be 9. So the corresponding partial sum that will give you the approximation within this accuracy will be S9. Because if you have n plus 1 here, An plus 1, with n is equal to 9, your n value is 9, so you have to plug in 9 here. So S9 is the approximation. You calculate, you go ahead and calculate your S9. Okay, if you calculate your S9, let me write. So the desired approximation is S9. Okay. Now I'm going to go ahead and calculate S9. S9 is, of course, you need to take the summation, right? Okay, to calculate S9, you need to, of course, take the 9 partial sum of the series. So basically, in this series, you plug in k is equal to 0, 1, 2, 3, 4, up to 9. Okay, so these are the terms that you will get. And if you take the summation using a calculator, you will see that this is approximately equal to this value. Okay, so this is an approximation to the actual value of the series within 10 to the power minus 6. Okay, and also notice that from the previous theorem, L minus Sn has the same sign as the sign of A9 plus 1. Okay, what is the sign of A9 plus 1? Oh, A9 plus 1 means A10. What is the sign of A10? Sign of A10 is plus, clearly, because if you plug in 10 here in this series to get the 10th term, you plug in 10 here, right? Minus 1 to the power 10 is plus 1. So that means it's a positive term. So this is going to be, sign is positive. That means the sign of this difference is also positive. It has a positive sign. That tells you that L is bigger than your partial sum. That means your L is little bigger than this number that you found over here. Okay. This is S9 actually, not Sn, S9. All right, that completes that example. Let's move on. Next, I want to go over these two definitions, absolute convergence and conditional convergence. Here is the definition of absolute convergence. The series k goes from sigma k goes from 1 to infinity bk is said to converge absolutely or equivalently be absolutely convergent if the series k goes from 1 to infinity, absolute value of bk converges. Okay, a given series is called absolutely convergent if the series with absolute value around bk is convergent. Okay, and here is the definition of a conditional convergence. Conditionally convergent sequence. A series sigma k goes from 1 to infinity bk is said to converge conditionally or be conditionally convergent if the series k goes from 1 to infinity, absolute value of bk diverges. Okay, your original series converges, but the absolute value series diverges. If that is the case, we say that it's a conditionally convergent series. Okay, again, an absolute, we say that a series is absolutely convergent if the absolute value series converges. Okay, that means this is absolutely converges if this series converges. This is the series by putting the absolute values around B. If this series converges, we say that the original series is absolutely convergent. And then conditionally converges means the original sequence series converges, but the absolute value series does not converge. If that is the case, we say that it's a conditionally convergent series. All right, let's move on. Next, I'm going to go over this theorem. Absolute convergence implies convergence. Okay, here is the statement of the theorem. If the series k goes from 1 to infinity bk converges absolutely, then it converges. Okay, let's quickly prove this theorem. We will show that if this series converges absolutely, then we will show that it converges. Okay, that means we need to show that if k goes from 1 to infinity, bk, absolute value of bk converges. That's what we mean by absolutely convergent. This sequence is absolutely convergent means this series has to be converges. This converges. Okay, if this converges, then the original series has to be convergent. Okay, let's prove this. So to show this, what I'm going to do is I'm going to start with some inequality. Okay, clearly for any k greater than or equal to 1, we have bk plus absolute value of, let me write, absolute value of bk plus bk is clearly greater than or equal to absolute value of bk plus absolute value of bk. Would you agree with me? All I'm saying is I'm replacing this bk by absolute value of bk, then I get a bigger quantity, right? Because absolute value of a number is always bigger than or equal to the number. Now this is nothing but 2 times absolute value of bk. Okay, this implies that by comparison test, notice that this is a sequence of non-negative numbers. This is also a sequence of non-negative numbers. Okay, this is a sequence of non-negative numbers, and this is also a sequence of non-negative numbers. But this term is bigger than or equal to this term. Okay, let me write this is greater than or equal to 0, of course. Okay, this term is bigger than or equal to this term. That means by comparison test, if this converges, this smaller series should also converge. Okay, but we know that sigma k goes from 1 to infinity, 2 times bk converges. Why is it? So if you pull out 2, you get k goes from 1 to infinity, absolute value of bk. Of course, we know that this is a convergent sequence, that we are assuming that. This is a convergent series, of course. We are assuming that. Okay, so this is a real number. This exists as a real number. That means this sequence, this series converges. Okay, if the bigger series converges by comparison test, the summation k goes from 1 to infinity, absolute value of bk plus bk also converges by comparison test. Sigma k goes from 1 to infinity, bk plus bk converges. Okay, now I'm going to do a rearrangement of terms in this. I'm going to write sigma k goes from 1 to infinity bk. This is what I need, right? I want to show that this is convergent. I'm going to rewrite this in a different way. Bk is the same as sigma k goes from 1 to infinity, absolute value of bk plus bk minus sigma k goes from 1 to infinity, absolute value of bk. Is this true? If you distribute this sigma sign inside the parentheses, you will get here sigma k goes from 1 to infinity, absolute value of bk. You have a minus of that here. So those two will be cancelled. You will just get sigma k goes from 1 to infinity bk. That is exactly the same thing as this one. But from the previous step, I know that this converges. We saw that this is convergent. So that means this series converges. And we also know that this converges by our hypothesis. We are assuming that that is convergent. Okay, so this is a convergent series. This is also a convergent series. The difference of two convergent series is, again, it exists as a finite number. Okay, so this converges. This whole thing converges. Does that prove what we want? Yes, this converges means your original series converges. Okay, this completes the proof. All right. By the way, the comparison test, I have put the comparison test here, if you don't remember it. Okay, let's move on. Next, we have this particular theorem, which is called the ratio test for absolute convergence. Okay, remember we did a ratio test in a previous section. This is very similar to what we did there. Okay, here is the statement of the theorem. Let k goes from 1 to infinity bk be a series with non-negative terms, and assume that rho is equal to this particular limit. Limit as k approaches to infinity, absolute value of bk plus 1 over bk. Okay, then here are the conclusions. If your rho value is less than 1, then the series converges absolutely. If your rho value is bigger than 1, then the series diverges. And if your rho value is 1, then we cannot use this test to determine anything. Okay, test is inconclusive. All right, now let me walk you through some examples to understand this theorem. Here is the example. Determine whether the series, this given series, converges absolutely, converge conditionally, or diverge. Okay, let's work on the first part. Part A. Okay, so how do we determine whether a sequence converges or diverges? The first step is always to check this. This is always an important thing that you can do in determining whether the series converges or diverges. You always calculate the limit as k approaches to infinity, ak. If this is not equal to 0, then you know the answer by the divergence test. But of course, if this is equal to 0, then you have to do some analysis to determine whether it is actually convergent or not. Okay, by divergence test, if this limit is not equal to 0, you always know that the series diverges. Okay, so first let's check this one. For this given series, what is your ak? AK is don't view this as an alternating series now. Okay, I'm just going to take my AK to be this whole thing, and I'm going to find that limit as k approaches to infinity and see whether I'm getting something that is not equal to 0. Okay, so how do you find the limit? Limit as k approaches to, let me put a question mark here. This is what I'm going to check to see whether I have an easy getaway. Okay, that means if this is not equal to 0, I'm done. I can conclude that my series diverges. Well, to find that, notice that limit as k approaches to infinity, minus 2 to the power k over 1 plus 2k is equal to 1 if your k is even. If k even. And limit as k approaches to infinity, minus 2 to the power k over 1 plus 2 to the power k is equal to minus 1 if k is odd. That means when k is approaching to infinity as an even number, your limit is 1. When k is approaching to infinity as an odd number, your limit is minus 1. So the limit does not exist, right? How can the limit exist? When k is getting bigger and bigger as even numbers, it is approaching to 1. When k is getting bigger and bigger as an odd number, it is approaching to minus 1. These are two different values. Okay, so the limit of the original series does not exist. This limit does not exist. Limit k approaches to infinity, minus 2 to the power k over 1 plus 2k does not exist. Because as k approaches to infinity, the values of the sequence is not approaching to the same value. When even, it is approaching to 1. When odd, when k is odd, it is approaching to a different value. Okay, it is not approaching the same value. So this limit does not exist. That means this is not equal to 0, right? This limit, this is your AK, by the way. This is your AK. Limit as k approaches to infinity, AK does not exist means this is not equal to 0. Now by divergence theorem, series diverges. By divergence theorem, pardon me, theorem, the series diverges. Series means k goes from 1 to infinity minus 2 over 1 minus 2 to the power k over 1 plus 2 to the power k diverges. Okay. As always, it is always a good practice to find the limit of ak. If ak does not approach to 0 as k goes to infinity, then you can immediately conclude that series diverges. Okay. And if you go to the second example, if you find the limit of this one as k goes to infinity, clearly it is 0 because your denominator is growing faster. So this whole thing goes to 0. That means you cannot apply the divergence test. Okay. If you want to apply the divergence test, then you need to have this limit not equal to 0. Okay. All right, let's do part B now. How do we deal with part B? Well, for part B, I'm going to show that this series converges by showing that this is absolutely convergent. If this series absolutely converges, then we know that it converges by this theorem. Notice that absolute convergence implies the convergence. If we can show that a series is absolutely convergent, of course, the original series also converges. Okay, that's what I'm going to do. So let's prove that this is absolutely convergent. To show that it is absolutely convergent, I'm going to get the corresponding absolute value series. Pardon me. K goes from 1 to infinity. Absolute value of minus 1 to the power k divided by k times ln k. When you take the absolute value, of course, this minus 1 is gone. Doesn't matter what power you have here. When you take the absolute value, it's always plus 1, right? So this is going to be equal to sigma k goes from 1 to infinity 1 over k times ln k. Notice that when, pardon me, here k goes from 2 to infinity, okay? Not 1 to infinity, 2 to infinity. That means k is bigger than or equal to 2. For any k bigger than or equal to 2, this is a positive quantity. Okay, so you don't need absolute value anymore. You just get rid of this minus 1 to the power k. All right, this is the series that we need to analyze. And notice that if I take, this is my ak, if I take ax to be 1 over x times ln x, I'm just plugging x for k. Then notice that this is a continuous function on the interval 2, infinity. And also notice that this function satisfies the criteria for the integral test. Okay, we can apply the integral test here, because if you evaluate this function when k is equal to 2, 3, 4, you will get the terms of this series clearly, and this function is continuous on this interval. So we can apply the integral test to determine whether the series converges. Okay, for that I'm going to calculate this particular integral. Integration 2 to infinity 1 over x times ln x dx. Of course, you need to use limits, because you have an improper integral here. Limit as b goes to infinity 2 to b. You take the limit b goes to infinity, then it will become infinity. Okay, 2 to b 1 over x times ln x dx. And you know how to calculate this limit, this integral, by calculus 2. And if you calculate this integral, you will see that that is infinity. That means this improper integral diverges. What does that tell you? By integral test, this series also should diverge. Okay. So 2 to infinity 1 over x times ln x dx diverges. That implies by integral test, I'll write IT, integral test, the series diverges. k goes from 1 to infinity minus 1 to the power k over k times ln k diverges. Pardon me, the absolute value of that series diverges. Okay, now we know that this series diverges. This series means the absolute value series. That series diverges. Okay, what about the original series? Okay, original series may or may not be the convergent, right? So we need to determine whether this converges or diverges. If this converges, if the original series converges, since the absolute value series diverges, we can conclude that it's a conditionally convergent series, right? So let's see whether this is a conditionally convergent series. For that, let's check whether this is convergent. Okay, if this is convergent, it is conditionally convergent. All right, to check that, notice that I'm going to view this as an alternating series. Here, this takes the form of an alternating series with my AK. Let me write here. Sigma k goes from 1 to infinity minus 1 to the power k over k times ln k is an alternating series with your AK is equal to 1 over k times ln k. Then AK plus 1 is equal to 1 over k plus 1 times ln k plus 1. I just plug in k plus 1 here and here to find my AK plus 1. Now notice that this denominator is bigger than the denominator here. Okay, because this k plus 1 is bigger than k, and ln k plus 1 is bigger than ln k when k is bigger than or equal to 2, because series goes from 2 to infinity, right? So what does that tell you? Let me go to the other page. That tells you that AK plus 1 is strictly less than AK for all k greater than or equal to 2. Okay. We also have limit as k approaches to infinity AK. Limit as k approaches to infinity AK. This takes the form 1 over infinity, that is 0. What does this tell us? By alternating series test, this original series converges, right? Because we have all the criteria satisfied. All the terms are positive. All the terms of this sequence is positive, and it is a decreasing sequence, and also the limit of that sequence is 0. So that means we can apply the alternating series test, and we conclude that sigma k goes from 1 to infinity minus 1 to the power k divided by k times ln k converges by alternating series test. Okay, what does that tell you? Few minutes ago, we showed that the absolute value series diverges. And now we showed that the original series converges. That means this is a conditionally convergent sequence. The conclusion is that this conditionally convergent series, pardon me, k goes from 1 to infinity minus 1 to the power k divided by k times ln k is conditionally convergent. Is a conditionally convergent series. That's the conclusion. Okay. All right. That completes that example. And I will leave the third part as an exercise, which is very similar to what we did here. Okay, here is the next theorem that I want to go over. Root test for absolute convergence. Remember, we did a root test in a previous section for convergence. Now we do a similar root test for absolute convergence. Okay, here is the statement of the theorem. Sigma k goes from 1 to infinity, ak be a series. We take sigma k goes from 1 to infinity, ak to be a series. And we assume that rho is equal to the limit of this sequence. This is the kth root of absolute value of ak, or this is in a different notation, limit k goes to infinity, absolute value of ak to the power 1 over k. Okay, we assume that this quantity exists and it is rho. Then here are the conclusions. If the value of rho is less than 1, the series converges absolutely. If the value of rho is bigger than 1, then the series diverges. And if the value of rho is 1, then the test is inconclusive. Okay. All right. Let's go over an example for this to understand this theorem. Here is the example that I want to look at. Use the root test for absolute convergence to analyze the given series. This is the given series. Okay. So I'm going to use the root test. To use the root test, I need to calculate this quantity, right? I need to calculate my rho. Rho is nothing but absolute value of ak to the power 1 over k. Okay, so this is my whole thing is my ak now. I'm going to find absolute value of ak to the power 1 over k. This is going to be equal to absolute value of minus 2 over k to the power k, whole thing to the power 1 over k. This is going to be equal to minus 2 to the power k, pardon me. You get rid of the minus power, 2 to the power k when you take the absolute value, of course, k to the power. Actually, we can do a little better here. Okay, this is going to be equal to minus 2 divided by k, the absolute value. I'm going to send the power k outside the absolute value. I can put this power k outside the absolute value, and then you take whole thing to the power 1 over k. Now, if you multiply this 1 over k times k, it becomes 1. This is going to be absolute value of minus 2 over k, which is 2 over k. Absolute value of minus 2 over k is just 2 over k. Okay. Now you take the limit. Limit as k approaches to infinity, absolute value of ak to the power 1 over k. This is going to be limit as k approaches to infinity, my iPad is not cooperating. Limit as k approaches to infinity, 2 over k is equal to 0. Okay. Now notice that this is the value of rho. Rho is 0. 0 means the value of rho is less than 1. That means the series converges absolutely. The given series, k goes from 1 to infinity, minus 2 over k to the power k, converges absolutely. By theorem 7.355. Okay, that completes that example. Actually, before we stop, let's go over the part C of the previous example that we did. I did these two parts. Let's work on this one as well. Okay. So for this one, I'm going to use the ratio test for absolute convergence. Okay. Recall that here is the ratio test for absolute convergence. If bk, sigma k goes from 1 to infinity, bk be a series with non-zero terms, and we assume that this limit exists. Limit k goes to infinity, absolute value of bk plus 1 over bk exists. And here are the conclusions. If this value of rho is less than 1, then the series converges absolutely. If the value of rho is bigger than 1, the series diverges. And if value of rho is 1, then the series, the test is inconclusive. Okay, so let's apply this theorem. Let's try to apply this theorem. For that, I'm going to identify my AK. My AK, pardon me, let's use the same notation as the notation in the theorem. Let's use BK for the series, okay? So I have BK here. So my BK in this case is going to be BK is minus 1 to the power k squared divided by k factorial bk plus 1 is equal to, you just replace your k by k plus 1, right, to get bk plus 1, k plus 1 squared divided by k plus 1 factorial. Now I need to find this quantity, rho. Okay, rho is equal to limit k goes to infinity bk plus 1 over bk. Bk plus 1 is, of course, absolute value of bk plus 1 divided by bk. Bk is minus 1 to the power k times k squared divided by k factorial. Okay, you need to simplify this. Okay, now you need to do some algebra, and of course you can get rid of this minus 1 powers because we are taking the absolute value. Okay, absolute value will kill all those minus 1 powers and it will make it positive. Okay, all right, so this is going to be equal to limit k goes to infinity. If you do the reciprocal rule, you will get k plus 1 squared divided by k plus 1 factorial times k factorial divided by k squared. Notice that I'm getting rid of all the negative powers. It will become positive because we are taking the absolute value, and I don't need the absolute value for this anymore because all the terms are positive. Okay, now you have certain cancellations here. This will be cancelled with first k factors here, and k plus 1 will survive in the bottom. Here, of course, you get k goes to infinity, k plus 1 squared over k squared, and then remember you have a k plus 1 in the bottom, additional k plus 1 in the bottom. Okay, this limit is clearly 0. Why is it 0?